You've probably seen this concept before. Generally speaking, you have some set A, right? You have some set A, and you have some set B, right? Some sets of things, and then you take so a function. Let me say like this function. Is a function. Function is function f, maybe going from A to B. So you read this as a function going from set A to set B, right? F mapping from set A to set B. Is a rule, say, which assigns to each element of A an element denoted fx of B. So it's a rule which assigns to each element of the first set some element of the second set, right? So the picture you have in your head is that for every point inside this first set, right, x, and then you have this thing f which maps over from A to B. It'll take x to some guy called f of x, right? If I have some guy here, A, it'll get mapped over to f of A, right? B, A2 gets mapped to f of A2. That's the notation. Okay. So it's something that takes in something, and then it spits out something in a well-defined, consistent manner. Okay. So it's not one thing about it is that it doesn't do this in an inconsistent way. It's not like if I give it, suppose I give it x and it says, I give it something and it says, oh, I will give you back this thing right now. And then the next time you put the same thing in, it gives you back something different. Okay, it's not so whimsical, right? It actually does. It actually makes this association in a consistent way. Okay? So assigns in a consistent blah blah blah, maybe in a consistent way. Okay. So So the notation, I'm sort of already introduced it. Usually people write something like this. F BR x gets mapped to f of x. This is pretty common notation for functions. F is a function going from the set D to the set R. D is something that we usually call the domain. Right? R is something that is usually called the range. Right? The domain is where you start from, and then the range is where you end up. And so f is a function. So this reads f is a function from domain D to range R, taking so assigning f of x, assigning to each x in R, x in D, f of x in R. Yeah, Rachel.
So using your arrow with the x to f of x looks different. Is that like a special?
Yeah, that's right. So there are lots of different arrows in math. So this arrow just means going from here to there. Okay. This arrow means is mapped to. X is mapped to. If this one is red, is mapped to. Or mapping this to that. Okay. right? So this is more like you have things here, and they get mapped inside here. But this is really, this gets associated with that. It's a more tight concept. Okay. So some examples. One, at the end of the term, I'm going to have a function. The function will be going from the set of math 30 students to a bunch of letters, right? A, B, C, D, F, right? And that will be a function, right? At the end of the course, there will be this function that I make that assigns everybody will be assigned a consistent grade, right? And it won't be whimsical, and it won't be inconsistent, right? It won't be that when you ask me one time, I say you got an A, and then when you ask me the next time, I say you got a B. Right? It's actually well defined. Okay. Let me give sort of a non-example. Do you know this thing, the Myers-Briggs personality test? Myers-Briggs personality test. So you might think that, like, to each person, to the set of people, right, set of all people in the world, right, there's supposed to be some function that goes to 16 possible outcomes, right? I, S, T, P, I, N, something, T, J, blah, blah, blah. So you get mapped to these personality types, right? And if the Myers-Briggs test makes sense, then this should be a well-defined function, right? To each person you get mapped onto something, one of these sets, right? But I find that actually every time I take it, I get a different response. I get a different answer. And so for me, this is not a function because it's not well defined, right? This wouldn't constitute a function because, at least for me, I get different answers. I get different personalities every time I take it, which may say something about my lack of personality or something. Okay. So so that I think would not be an example of a function. Another example, maybe more straightforward this time, going from the non-negative real numbers, so the real numbers that are greater than or equal to 0, okay, and taking x to the square root of x, okay, to the positive square root of x. Okay, that's a function, right? This usually denotes the positive square root of x. Okay. That's well defined. To every positive number, it associates the positive square root. Okay. Right? I should remark that usually you just write this. This may be how you've seen it in the past, right? People just write f of x is the square root of x, rather than this full-blown description, right? And then you just assume, you say, oh, what's the domain? One just assumes the domain to be as large as possible, right? So if you don't give the full-blown description, then one abbreviates like this with the domain assumed to be as large as possible. Okay. Right, because you could define the square root function on a smaller domain. Like we could say the real number is greater than 10. Right? That's okay. That's a function. Going from the real number is greater than 10, right? That's an okay function, but that's not the largest. That's, if you write it like this, generally we're assuming the largest domain possible. So that would be this. Can you reach?
Yeah.
Yes.
So if you have square root of x, wouldn't you have to restrict the domain so that it's only positive values?
You restrict the domain to the positive reals because in this course at least we're not going to take the square roots of negative numbers. Okay, but you don't. But this generally denotes the positive square roots.
No, but I was talking about the f of x values because if you like, for example, the square root of 4, it's
That's right, that's right. So this function is going to only the positive. This thing denotes only the positive root.
So, okay,
Yeah. So you could have some other function, right? G, and that guy gives you the negative roots. Okay. That if I wrote something like this, then that would mean you're going to the negative, like this would say G to 4 would be negative 2. Okay. Yeah. You have another question? Yeah, go ahead.
So if you didn't restrict the domain, and if you didn't give any specifications, so then root of x would not be a function because it would have 2 outputs for every input.
So, well, so there's two things that's not quite right. It's not a matter of restricting the domain, but rather specifying the output. Okay. So it's not that it's not that because I've restricted the domain, I'm okay over here, right? It's rather because I specified it what it is over here, I'm okay, right? I'm saying that if I write f of x is the square root of x, then I'm talking about the positive square roots of x. Okay. So it's true that if one talks about square roots of x in general, there's a plus and there's a minus guy. Okay, but when in mathematics, when one uses the square root sign, that means that always means actually the positive square root, at least in this class. Okay, so just by writing this thing, I've specified that we're using the positive square root. Okay. And then the second thing that's I've forgotten what you said, but so I'm not sure what the second thing was that I wanted to say. I'm sorry.
Basically for negative. So you specialize the points that you would get negative outputs on the bottom. So you didn't change the domain. It was just
yeah. All I'm doing is I'm describing the function here. As long as I've described the output property, then I don't have to worry about. It's not a matter of like, does this square root mean the positive or negative one? Does this square root mean the positive or negative one? It always means the positive one. Okay. It always means the positive one. Although it's true in general, if you're talking about the square root of a number, then you could have plus or minus something. Okay. So, right. So I mean, it's a little bit confusing, but you could, right? It's true that the square roots of 4 are positive the square root of 2 and negative the square root of 2. Okay. Sorry. Positive 2, sorry. Positive 2 and negative 2. Okay. Positive 2 and negative 2. Okay. Yeah. That tends to be a point of confusion at the beginning. Just remember that whenever we write the square root, we're talking about the positive one. Okay. Okay. Let's see. So I'm going to make one comment about a term, image. So there's a term called range and a term called image. Okay, and sometimes people conflate these terms, but there's actually a difference. So difference between range and image. Okay, so range is really a set that contains all outputs of the function. Okay, it's basically any set that contains all outputs of the function. Okay, so if I'm talking about the square root function, right, f of x is the positive square root of x, then you could write f goes from this domain into, well, you know, what kind of outputs does this function give you? What kind of outputs does it give you? Positive or really non-negative, to be precise, non-negative real numbers, right? So if I write R is the range, that's actually a valid statement, right? I could write, one could write, R is the range, right? Because that contains all the outputs. Okay, hold on one second, Rachel. Hold on one second. Okay, that contains all the outputs. Okay, but really, the actual outputs are only the non-negative numbers, right? The image. So the image is the set the set of outputs. Okay, so for the square root function, the image of f is the non-negative reals. Okay, so it is the actual outputs, and the range is just something that contains the actual outputs. Okay. So generally, when you write something like this, you don't have to be so precise about the range, right? You could just say, oh, it's all of R, right? I could just have written, well, I could write, oh, the range is the real numbers, right? Just meaning that the outputs lie in the real numbers. Okay. Although it's more precise to say, it would have been more precise to say that the outputs are lie in the non-negative real numbers. Okay. Anyway, just a fine point to distinguish these two terms. Rachel.
Can you re-explain when you do the f colon real numbers greater than or equal to 0 with the arrow and then other real numbers? What does that mean?
Like, what does that mean? This means you have this function, its domain is this, and its range is this. Okay. F, right? You've got the square root function. We could say it's a function that takes in non-negative reals, and it gives you back real numbers, right? That's true. Okay, don't worry too much about that. It's just a fine point. Okay. I don't think you have to worry too much about it. Okay. So. Yeah. Okay, so let me put the last example. F goes from the non-negative reals to the reals, and to every x it associates x over x plus 1. Okay. To every number x, right? So it takes in a non-negative number, and then it gives you back this ratio, the number over 1 plus the number. Okay. Okay. So just to make you think a little bit, what is the range? No, what is the image? The range is easy, right? You could say just like all real numbers, right? Certainly, what it gives you back is a real number. So range is easy to describe. But if we wanted to describe the image, what is exactly the outputs, the set of all outputs? I'd like you to think about it. Think about it for about a minute or so. Okay? See if you can figure out what the image actually is. Okay. What can you get? What can't you get? Maybe that's one way to think about it. What can you not get? What kind of numbers can you not get? And if you take the complement of that, that will tell you what you can get. Okay. So I'm going to go walk around. Think for 1 minute, please.
Okay, that's also the problem, because I think you have negative 1 in the denominator. Anyways, it's not the case.
Okay, who would like to make some? We'll take some guesses. What is the image? Eliza.
All real numbers except -1.
All real numbers except for -1. So all real numbers, but not negative 1. Okay. Rachel?
I thought you were restricting the inputs to positive.
That's right. The inputs are only the non-negative numbers.
So then can't you only get things that are positive?
Okay. So shouldn't you be only getting positive numbers, right? Because you're putting in a positive number and you're getting out a positive number over that number plus 1, right? So it should be. So at least we should be numbers greater than or equal to 0, right? Maya?
We were thinking that is y is greater than or equal to 0 and less than 1.
Greater than or equal to 0, and so f of x is greater than or equal to 0 and less than 1. Right, so the interval 0, 1. Okay. Other guesses? Okay. You guys are right. So yeah, should I give a bonus point for that? Maybe. Except you got one the other day. I'll give both of you half a point. I should give. Why are you stingy? I should give you both 1 point. Yeah. So why does that make sense? Why does it make sense? Well, you think, okay, well, right. What's this? You see that if you feed it a positive number, you're going to get out a positive number, right? So everything's going to be greater than or equal to 0. That's clear, right? And then, right, if you feed a 0, well, then you get 0, right? So you know that 0 is in there, and you sort of see that you can get this thing. You always have. Well, I mean, I should probably let you two explain it. So why do you say why is 1 the upper bound? Say.
Sure. So as x gets greater and greater, it's
Mhm.
gonna like approach 1, but it's never gonna hit 1.
Yeah,
because
yeah.
It's always gonna be a fraction.
Yeah.
less than 1.
Yeah. So one thing you see is that this number is always less than 1, right? Because the bottom is always bigger than the top, right? But you never get to 1 because the bottom is greater than the top, right? But as you take larger and larger numbers, they get closer and closer to the number 1, right? And you start from 0, and your numbers get bigger and bigger and closer to 1. Okay, so that is the actual image of this function. Although we sloppily said that the range was R, which is true. So here we've written the range as R. The image is actually this interval 0, 1. Okay. Any questions? Okay. Okay, so this is really a matter of just notation. There are these things called piecewise defined functions. Piecewise defined functions. And it's just who was that guy? Okay. Let me give you an example. There's this thing called the Signum Function, and when one defines it like this, you say the Signum Function is going to give you a 1 if x is bigger than 0, it'll give you a 0. If x equals 0, it'll give you a -1 if x is less than 0. Okay, so piecewise defined functions simply means that it's defined in pieces. It doesn't have a definition that works for all numbers, but rather you split the domain into parts, right? Right, where x is bigger than 0, it's this value. Where x is equal to 0, it's this. Where x is less than equal, it's this. Less than 0, it's equal to this. Okay, that's basically it. I mean, you could, you can make up piecewise defined functions. You could say my function is a parabola whenever x is greater than 5. but it is the Signum function when x is less than or equal to 5. Okay. Right, so this guy would be the Signum function up until a certain point, and then suddenly changes into a parabola. Right. So this is how you describe functions. Right. You write down write down these basically notation descriptions which you translate into English. Okay. Okay. So as you no doubt know, there's a way of visualizing functions, and it's by using these things called graphs. Right? Graphs of functions. Okay. So function, and I always abbreviate function fn dot. So a function is really a map, right? This sort of map from one set to another set, right? But for f going from R to R, one has a useful tool, the graph of the function, right? This thing called the graph. Okay. So given a function, okay. So given a function, let's say going from R to R, we associate with it a set, and this set is x, y in R2 such that y equals f of x. Okay. The graph of f. Okay, so we have this function, right? Let me use the Signum function as an example, okay? So for example, f of x is the Signum function, right? Really the Signum function looks something like this, right? 1, 0, negative 1, right? It says whenever you take a positive number, map it to 1. Whenever you take so it's a 0, you have a positive number, map it to 1, map to 1, map all these guys to 1, map 0 to 0, and map everything else to negative 1. Right? All the negative numbers get mapped to negative 1. Right? So as a mapping, this is how the Signum function looks. Right? Positive guys get mapped to 1, negative guys get mapped to negative 1, 0 gets mapped to 0. Okay? That's exactly what it is, right? But as you know, we also have this thing where we take the domain and lay it sideways, right? We take the domain and lay it sideways, and we take the range and put it perpendicular to the domain, right? So this is the domain, R, the domain, and this is R, the range, right? And what we do is we say we're going to take all points where y is f of x, right? We'll take all points x, y, where y is f of x, right? So for example, 1, 1 is on our graph, right? Because 1, is on our graph because y is f of x, right? Y is f of x. 2, 1 is on our graph because 2, 1 is on our graph because y is the Signum function of x, right? In fact, if you take any positive number, right, all these guys lie on the graph, right? Because for any number p, right, p1 lies on the graph, right? Because y is the sign of this positive number. 1 is the sign of this positive number. Right. Of course, 0, 0 lies on your graph because signum of 0 is 0, right? And everybody over here lies on your graph, right? Because if you put in a negative number, right? If you take some negative number n, then n comma negative 1 satisfies this relation, right? Negative 1 is the sign of your negative number. Okay. So this is maybe not exactly how you thought of graphs, but this is the same. This is actually the same way that you've learned before, just from a slightly different viewpoint. Okay, right? Probably when you saw graphs before, you thought of it in the opposite way. You say, I come to here, and then I go to that height, and that height is going to be y, right? That height is going to be f of x. That's the same thing, right? That's exactly the same thing. I'm just asking you to look at it from the opposite point of view. Right. Look at, it's like you can look at me this way, or you can look at me this way. It's the same thing. Okay. 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 So let's see. Right. So another example. F of x is the square root of x, right? Right. Then your domain is the non-negatives, right? The non-negative reals here, right? And let's just do it the more straightforward way. You say, okay, what point? If this is 1, then I'm going to go up to the square root of 1, which is 1. 1. Okay. At each point x, I'm going to go up to. I'm going to include the point x comma square root of x. Right? So every point, to every input here, I'm going to include the corresponding. If this is 4, then this is going to be 4 comma square root of 4. Right? And you get this thing in the graph. Okay. But the point is that for xy to be on the graph of f means exactly that y is f of x.
Bless you.
Right. xy is on the graph means that y is equal to f of x. Okay. So let me put up an example for you to think about. I'm destroying talk, which usually means that I'm excited, but not this time. This is not interesting. I'm joking. Okay, so suppose you have some function here. Okay, so here is the graph of some function. Some function f. Okay. Okay. And this is the line y equals x. So this dotted line is y equals x. Okay. If I start out at A and I go up to here and I go to the line and I go up to here, what are the coordinates of this point? So just to sort of test if you're understanding what it means to be on a graph, here's a question that will make sure of that. Okay. Here's the graph of f. This line is the graph of f. This line is y equals x, and you're going to start at some value a and just go up perpendicularly until you hit the graph. So maybe the first question is, what's the coordinate of that? Second question, what are the coordinates of this point? So then go perpendicularly over here, right? And then go perpendicularly up to here. So what are the coordinates of these 3 points? Okay. And if you know what a graph, if you're understanding the meaning of the graph, then it'll be clear. Okay. And if not, just think about it, and then you'll understand the meaning of the graph. So take a minute or so.
Oh, yeah.
Can you share with somebody next to you and talk, or somebody behind you if there's somebody next to you?
That's the graph of y. Well, I mean, basically those numbers you see like this. Yeah. Right.
Okay. Who would like to give an answer? Who would like to give a guess? What's this first point here? This is A. What's this point?
F of A.
The y value is f of A. Yeah. So the x is A. So this guy is f is A f of A. Mm-hmm. Right. Okay. What about this second point? Right. Well, what's its? What it, Michelle? Yeah, but what are x and y? Right? We can say more precisely. Right? The height is f of a, right? The y value is f of a. Alfred?
Is it
F of a, right? Because it's on the line y equals x. Lying on this line means that you satisfy y equals x, right? So we know that the y value is f of a. That means that the x value is f of a. Okay. Richka?
Why would the x value be f of a?
Well, so the y value is f of a, right?
Alright, so y value is f of a.
Right. And this point is on the line. Where is this guy? It's on this line. The line y equals x.
Okay.
Right.
But why is x f of a? I'm not understanding what the x value is.
Because to lie on this. Right, to lie in this line means that your y value and your x value must be the same, right? So we know the y value, thus we know the x value.
Okay.
Okay, and then so what's this point now? Shravya, please? Is that your name?
No.
No,
Yeah,
so what's your
yeah.
name?
No, obviously I just don't know the answer.
Okay. Okay, but you said something. Do you want to say something again? Or not?
F of A, and do you know what the y value would be for that?
The x value is f of a, and it lies on the graph of f, right? Lying on the graph of f means that the y value must be f of the x value,
So
right?
F of A.
F of a, exactly. Okay. Right. And if we kept on going, right, yeah, we would get f of f of f of f of f of, right? It would keep on, if we kept on zigzagging like this, we would get, guys that look like f of f of f of a, and then the second one would be the same thing, but one more f, right? Right, you keep on going. Okay. Okay. Right. Okay. So just to make sure, everybody thinks they know what graphs are, but I think this makes it clear. It makes it even more clear what a graph means. What does the graph mean? Okay. Okay. So okay. So yeah. So just one remark. One can do this in other dimensions. Right, you could have some function going from R2 to R, right? Some function going from the plane to R. You could have some function going from R into the plane, et cetera, et cetera. Right? But in this class, we're only going to stick with functions going from one variable to a single variable. Okay? And something else that you've probably seen before, does every curve in R2 exist as correspond to a function? Right? Is every curve a graph of some function that you know the answer to? I assume. What's the answer? Is every curve a graph of some function? Like here, I've got this curve. That's going to be the graph of some function? No, right? What needs to happen? It has to satisfy the so-called vertical line test, right? So no, right? Must satisfy vertical line test. Right? And that's basically another, just another way of saying that the function must be well defined. Right? If you give it an input, there is only going to be one output. It's not that you give it some input and then there are many possible outputs. That's all right. Okay, right. This would, for something like this, there would be, oh, I don't know what the answer is. Is this f of x? Is this f of x? Or is this f of x? Right? All these points lie on the supposed graph. Well, that would mean that this y is f of x, but then this y is f of x, and this y is f of x too. It's not well defined. Okay, so this is not a function. Okay, that you know. Okay, okay. So just in the last few minutes, let me talk about the simplest sorts of functions, which are called sequences. So sequences. Now these guys are functions going from the natural numbers to the reals, say. Okay. Right. Natural numbers you would call 1, 2, 3, 4, 5, etc. Right. And so to each natural number, and usually one denotes a sequence not by f but by an a or b or something. Okay. So to each natural number, it'll associate some number. Okay. So okay, and I should say that one usually doesn't use the function notation, but one uses a subscript notation. Okay, so instead of writing a of n, you write a sub n. This is usually written a sub n. Okay, so in a simple example, a of n, a sub n is, say, 2n, right, for n and a natural number. Okay. So if I write this, what it means is that I'm talking about the function a1 is 2, a2 is 4, a3 is 6, a4 is 8, etc., etc. Right? Okay. Right. So this is the guy that takes in a natural number and then returns double that natural number. You take 1, gives you 2, takes 2, gives you 4, takes 3, 6, etc., etc. Now you could have something like a sub n equals 2n minus 1, and the natural numbers. Right? What does that give you? What kind of stuff does that give you?
Odd number.
That gives you all the odd numbers. Right? A1 is 1, A2 is going to be double 2 minus 1, so that's 3. A3 is going to be double 3 minus 1, that's 5, etc., etc. So that gives you all the odd numbers, right? Right. You could have something like this. an is going to be n plus 1 over 2 if n is odd. So we could make a piecewise negative n over 2 if n is even. Okay. So for example, a of, I'm going to start with 0, just for convenience. A of 0 is 0, a1 will give me 1, a2 is going to give me negative 1, a3 is going to give me 2, a4 is going to give me negative 2, etc., etc. Yeah, Emily?
How would you graph that? Like decimals and stuff, the points in between?
Yeah, so the graph does it basically in the same way. Here's the domain, right? Here's the domain, but your domain is really dots, right? 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, blah, blah, blah. And so A0 gives me 0, A1 gives me 1, A2 gives me negative 1, A3 gives me 2, etc., etc. It's just going to be dot. We won't get a curve now. It's just going to be isolated dots. Yeah, for the same thing. Okay. So this sequence, you see what this sequence does, right? This is really a mapping from 0, 1, 2, 3 onwards onto the integers, right? Okay, onto the integers, etc., etc. Okay, so let me finish up with another way of defining sequences. You can use what's called a recursive definition. So it's pretty simple. I'll just give you an example. This is the famous Fibonacci sequence, which is defined like this. You say A1 is 1. You define it. A2 is also defined to be 1. Okay. Then AN in general is AN minus 1 plus AN minus 2 for whenever n is bigger than 2. Okay. So for A1 and A2, you define it, and then above that, you define AN in terms of the two previous guys. Okay, so AN is defined as the sum of the two previous guys. Right? You see why we had to define the first two, because you need two previous guys to get A3. Right? So you see how this works. Right? A3 then is going to be, you say, oh look, n is bigger than 2, so this is going to be A2 plus A1. That's to say 1 plus 1, 2. Right? A4 is going to be A3 plus A2. Right? So A3 plus A2, that's 3. Right? A5 is going to be the sum of the two previous guys, that's 5. A6 is going to be the sum of the two previous guys, that's 8. Sum of the two previous guys, sum of the two previous guys, sum of the two previous guys, etc., etc. Okay, let's stop here for today.